A very good evening to everyone that's joining us today. I welcome you all to the next webinar in the IRIS 2.0 webinar series. So today we'll be focusing on the Center of Excellence in Maritime Experiments to Maritime Experiences, aka ME2ME. ME2ME is a collaborative initiative at the Department of Ocean Engineering, IIT Madras, synergizing the strengths of three IOE centers of excellence, which are CMAS, the Center for Marine Autonomous Systems, CFLOR, Center for Large Scale Ocean Research, and SMATE, Center for SMART Maritime Technology. With a steadfast commitment to autonomy, digitalization, and ocean analytics, ME2ME endeavors to redefine the landscape of maritime infrastructure. Picture autonomous vessels traversing the vast expanses of the ocean, intelligent port-side infrastructure optimizing operations, and cutting-edge testing facilities pushing the boundaries of technological innovation. Through strategic international collaborations and pioneering research endeavors, ME2ME aims to elevate the global standing of IIT Madras, solidifying its stature as a preeminent leader in the realm of ocean engineering. Without further ado, let me now introduce our distinguished panelists for today's program. First up, we have Professor V. Sriram, Principal Investigator at ME2ME, who brings extensive expertise in ocean engineering, specializing in numerical model development and its application in ship simulations, offshore structures, and coastal engineering. With a PhD from IIT Madras and prestigious international fellowships in the UK and Germany, Professor Sriram has earned accolades, including the R.J. Gade Research Award and the ISOP Conference Best Session Organizer Award. His research focuses on understanding extreme wave interactions with marine structures, vital for advancing renewable energy sustainability. Also, we are honored to have Dr. Abhilash, Co-Principal Investigator and Director for the Center for Marine Autonomous Vehicles at IIT Madras, and his expertise is in marine autonomous vehicles and artificial intelligence for maritime systems. With a PhD from Texas A&M University and certifications in robotics and machine learning, his research spans system identification, hydrodynamics, and nonlinear time domain simulations for floating systems. Dr. Abhilash's pioneering work includes projects on designing an autonomous surface vehicle, developing the hydrodynamic simulation tool, and investigating the parametric role of container ships, showing his commitment to advancing marine engineering technologies. Completing our esteemed panel is Dr. R. Suresh, co-principal investigator who specializes in numerical and experimental modeling of fluid structure interactions, autonomous marine vehicles, and the application of AI and ML to ocean engineering. With a distinguished academic background, including a PhD in naval architecture and marine engineering from Instituto Superior Técnico, Lisbon, Portugal, and extensive professional experience in research and industry, he brings a wealth of expertise to his work. His research interests encompass a wide range of topics, such as ship dynamics, hydrodynamics, and hydroelasticity, making him a leading figure in the field of ocean engineering. It's now my honor and pleasure to welcome our moderator for today, Professor Antonio Pascal. Professor Antonio Pascal is a distinguished educator and researcher specializing in control systems and robotics at IST, University of Lisbon. His expertise lies in dynamical systems theory and aerial ocean robotics, with a focus on navigation, guidance, and control of autonomous vehicles. As an adjunct scientist with the National Institute of Oceanography in Goa, India, he contributes to the development of advanced robotic systems for ocean exploration and exploitation. With a PhD in control science from the University of Minnesota and extensive experience in academia and industry, he has led numerous international projects aimed at designing, developing, and field testing autonomous marine and air vehicle systems. I once again welcome the entire ME2ME team and invite Professor Sriram to start our session for the day.
Thank you, Danya, for starting the session as well as for the nice introduction of all the speakers. I would like to also thank Professor Antonia for moderating our session as well as for collaborating with our group at IIT Madras for the last few years. So I will try to first introduce about this particular center, which is ME2ME, which we call as a Maritime Experiments to Maritime Experience. We have a group of faculty from IIT Madras, from Department of Ocean Engineering. We put together this particular proposal for bringing some of the visionary stuff in India, particularly. So my colleagues, Dr. Abhilash, Professor Murali, Sana Siraj, Dr. Vijay Kumar, Suresh, and Arjun were part of this particular center, wherein we try to do some of the innovative and state-of-the-art research at IIT Madras. So I will just try to give you an overall picture about what we are doing at this particular center. And then I think, and then Professor Abhilash will try to give you in-depth detail in one particular area, because we could not able to concentrate on all the areas wherein we would like to, we are right now focusing on. But if any one of the participants are interested in looking at one of the aspect, we will be happy to answer your questions. So, so that is all overall this part. So if you look at this ME2ME vision, so what we are planning to do is we would like to create a global hub, particularly in India, for marine research as well as for the industrial solution. It can vary from green technologies like offshore wind, wave, as well as solar, as well as particularly for the deep sea technologies for energy, as well as for mineral, as well as for the defense, as well as if you look at one of the Maritime India vision, that is 2030 from Ministry of Shipping, Ports and Waterways, wherein they have a vision of creating deep drafted ports. That means you have to create a lot of innovative technologies as well as from the solutions to that, and the investment is of in a million euros particularly. And more importantly, ocean engineering, if you look at it, because of the climate change as well as a lot of morphodynamics that is going to that is actually taking place in the ocean, which actually try to change most of the coastal engineering as well as offshore structural design aspect, that is hydrodynamics aspect, as well as the other scenarios. So that is also we would like to look into it, along with disaster management plan. Whenever there is going to be a storm surge, how to protect using the latest state-of-the-art AI as well as machine learning tools. How do we can actually predict these weather forecasts? Even that is also one of the aspect to it. Along with that, we are also looking at the autonomous vessels, surface vessels, autonomous underwater vessel, that is basically comes under marine autonomy. So the second part of this entire webinar will be concentrated more on the marine autonomy, so, to be very precise. But if you look at the IRIS one webinar series, wherein we have 3 different centers, so you can actually look into each of the details of these 3 centers. That is basically SMART Maritime, the technologies, wherein you have a detailed discussion for 1 hour for this entire part, as well as the same thing with the CFLOR as well as the CMAS. We have separate 1 hour webinar series. So we all merge together. That is why we call this experiments. If you look at this particular say, we do experiments in the laboratory scale, as well as we want to go into the field. So that is why we say this is a Maritime Experiments to the Maritime Experience. So that is what we call this center as this part. And one of the goal of this particular center is not only creating technological products, but also to create one of the world's largest facility, which is going to be part of this particular center. As well as we would like, once you create that particular kind of facilities, we will also try to create an international alliance with the leading research groups around the world, as well as try to experience to the industrial link. So that was the overall goal or overall the vision of this particular center. We would like to expand from both from offshore to coastal to the naval architecture industry. So that is what we try to look into it. So if you look at, just to give a brief introduction about this, what is this ocean engineering contest? If you look at it, this particular slides try to give you what are the different types of scale wherein a ocean engineer is trying to look into it. There is going to be 2 different scale. One is in the time scale, the other one is the horizontal spatial scale. So the physical problem is going to depend on the scales. Okay, what type of physical problem you are trying to look at. Suppose if you look at it in the large scale, that means the time scale is 100 years. Of course, it is going to be a global scale event like a sea level rise or the climate change scenarios. So for those things, we need a global scale modeling or a region scale modeling. Wherein if you try to look into the other scales wherein there is going to be wave structure interaction is going to be dominant, like for example ship maneuvering or wave breaking, or for example hydroelasticity or the turbulence. All those things are basically going to be in the small scale, which is going to be in seconds to minutes. And of course the horizontal spatial scale will be in kilometers, so it depends upon what type of problem you are trying to attack. So if you look at it, we have scales, the time scale ranging from 1 seconds to 100 years even, as well as we have a horizontal spatial scale from millimeter to a kilometer. So this is the overall complexity of ocean engineering, whether it's offshore or a coastal or a naval architecture part of it. So whenever you try to model these aspects, we have to, of course, people try to do it either by using analytical approximation, or they will try to do using a numerical approximation, or by using a small scale, or by using a small scale experiments. So what we will try to, so what we will try to do here is, normally we will try to do a approximation, because we cannot able to address all these scales as well as the spatial scale, because the non-linearity and everything will be high enough, as well as the domain scale modeling itself will be challenging. So that means people try to do a lot of approximations, like reducing the order of the equations that you are trying to deal. That is what analytically as well as people do it numerically. Of course, whenever you try to do this in the model scale, there is obviously going to be scale effects. I will talk about that in a minute time. And of course, you need, the recent scenario says that there is a lot of extreme events that are happening. So we have to look into these extreme scenarios also into the modeling aspect. So either you can do a numerical modeling, or you can actually do a experimental modeling in overall addressing the understanding this entire physical process.
Change the mic
there. Is it?
Yeah, so you can mute that. I'll unmute this.
You can hear me? Yeah. You can hear me?
There's a lot of echo.
There is an echo.
Now it seems to have gone.
Yeah,
When
now
you-
it looks fine. Sriram is muted.
Maybe you can turn either one of your mics, Professor.
No.
Oh, the room mic is switched on, looks like.
Muted. How do you mute?
Yeah, this looks fine. I think Sriram's mic is fine.
1 second. Is it muted now?
No, this is fine.
This is fine.
Mute the.
No, you're muted now.
Okay, are we audible?
Yeah,
Yes.
good.
Can you able to hear?
Stay muted. Stay muted there. Stay muted there. Are we audible now?
Yes.
1 second. Are we audible?
Yes, Professor. Yeah.
Yes,
Is it
you are
fine?
fine. You are fine.
Yeah. Okay. So, okay, I will. Is it okay now?
Yes.
Yeah. You have. Yeah. So you can. There is no echo, correct? Yeah.
No, there's no more echo. This is fine.
Yeah. Sure.
Okay.
Thank you. Thanks. Yeah. Okay. Sorry for the interruption. So, one of the aspect is how do we model this entire scenario. So one way you can able to overcome this is try to go for a large scale model, because we have two different scales, that is a large physical scale as well as the spatial scale as well as the time scale model. So because the scale effects is going to play a role, particularly in the coastal engineering, for example. So one way to do this is try to construct a address this entire scenario by decreasing the error. If you look at it, for example, the scale of heights, particularly this particular scale of heights, you have a different type of scale of height. That is the forces that we have to satisfy is the gravity, friction, elasticity, and surface tension. So in order to satisfy each of these effects, of course, you have to do a modeling law. If you look at 1:1 scale, all this entire scenario will try to get satisfied. But if you go to a smaller scale, or if you try to do it at a different scale, obviously there is going to be a scale effects that comes into picture. So to address this particular problem, people have went for a large scale testing facility in the world. So if you look at it, these large scale facilities, there are only a handful of large scale facilities that are available, particularly for a coastal engineering. We are talking right now over here is a 1:1 scale of water depth of 5 meter. If anything that can able to do it in a 5 meter in the field, that we can able to reproduce that same at 5 meter depth. Means if you can able to do it for different water depth, you will have a different scale effect. But up to 5 meter, you can actually do it in the same scale. So that was the overall idea. So if you look at it, there are different facilities that actually built from GWK plus and new Delta Flume. All those things can able to handle a very high water depth, and we can able to generate a 1:1 scale facility. So as part of this center, we actually proposed a 500-meter long flume that is under plan right now. We are trying to we got the space and we are trying to build this particular facility, which will be part of this entire center. So we actually have where we are going to have this particular large scale facility in India. This is going to be one of its kind in India, wherein we are going to have this facility in the Discovery campus, which is quite 40 kilometers from the present campus at IIT Madras. And we have two different scenarios. That is, we have seen that there is a C building and D building. C is basically a port center, which we are right now inaugurated last year. It is completely, which is in operation right now. This is one of the Asia's largest shallow water basin facility, wherein you can actually vary the water depth from 35 centimeter to 1 meter. Of course, you can also do the maneuvering studies, all those things in the large basin. And this entire facility was completely in-house developed, which is having 142 waymakers that can actually operate in any synchronized motion, whichever we want to do. So this cost of the facility is it's completely in-house developed, and we have not even imported any of those knowledge which is coming from this particular facility. And this is one of the key thing wherein we can able to create such a large facility at the campus. That is basically the deep part. So parallelly, we are also trying to do another facility which is part of this particular shallow wave basin, which is an intermediate testing facility, wherein this is of 1:4 scale. Again, this facility will be used for testing, of course, any offshore wind, as well as for the floating sector, as well as for the breakwater in a 1:2 in a little bit medium scale, that is basically mid scale facilities. So we have a stroke length of 4 meter that can able to generate a wave period from 3 to 6 seconds. But of course, we cannot able to do any maneuvering over here, but we can able to do from motion studies or sea keeping part of it mostly over here. And the final one, which we are having a vision of creating one of the largest testing facilities, which have a stroke of about 8 meter. That is what we are right now planning, and which can able to create a significant wave height up to 3 meter, exactly 1:1 in a prototype condition with the 4 seconds to 20 seconds. So that means we have a very big paddle to push the entire water column of this wave. So this is a testing facility which we have in mind, and some of the key knowledge or key technology areas that we try to address using either using this facility or using our own expertise on autonomous surface vessel, as well as for the renewable energies, as well as for the dynamic, that is in the coastal engineering, particularly the scour, as well as the bed evaluation, as well as the ecosystem based solution, that is basically the wave vegetation interaction, as well as we will try to address the inland waterways. Particularly the inland waterways are trying to boom. I mean, it is going to have a big boom in India right now. So we would like to analyze a tool to stabilize this bank when the inland waterways are going to take place. And then, of course, we are also looking at closely on the vessel traffic management system as well as the e-navigation system as well as the maritime digitalization. These are all already put forth in some of the ports in India. And I will try to list out some of the research verticals that we will be working on this particular center. In the next 15 minutes, I think Professor Abhilash will discuss more about this autonomy and AI. So I will just, this is one of the area which we will try to look into it. As well as the state-of-the-art numerical models which we are having at present at IIT Madras. We have all our own in-depth in-house developed numerical models, stating from fully nonlinear potential flow solver to the Boosnick's model to the shallow water equation model, as well as the WaveGen, as well as the simulator. All those things, some of those things are basically state-of-the-art numerical models, which we have actually benchmarked with a lot of other codes internationally. And this is one of the highlight of this particular center, wherein we have a collaboration with a lot of people around the world, wherein we actually try to do a benchmarking of our code along with the rest of the world code. So that means we are actually in the field for some time. And other research vertical which we are trying to work on is on the survivability of the renewable energies. One of the issues, of course, yes, we can put a renewable energy over there, but particularly in India, if you put it in Bay of Bengal or near to Kanyakumari, the survival of those particular renewable energies, because we are actually facing some extreme climate scenarios. So how during those extreme climate scenarios, these wave energies will be survived. So that is also one of the research area. As well as we are also working on the AUV docking. Again, I think Professor Abhilash will try to look into this aspect in the next 15 minutes of talk. And apart from these autonomous vehicle as well as the autonomy, we are also looking into the coastal engineering, particularly the extreme climate scenarios, the nearshore morphodynamics, and the data science in the ships, as well as in offshore engineering, as well as the green ship initiative, particularly the air lubrication system under the vessel in the inland waterways to try to reduce the drag. Okay, so that is also one of the part which we are trying to look at as part of this center. Recently, we also transformed some of those research into industry. Particularly, we also as part through this center funding, we also try to integrated the real-time dredging monitoring system, as well as maritime digital twins for some of the ports like Kamarajar Port and Paradip Port, which we have already implemented. And currently, we are also implementing these real-time dredge monitoring systems to some of the ports. So it means not only the research part, we also try to transform this to the industry. And particularly the next aspect is we also try to develop e-navigation system for the national waterways, which has been implemented in the first phase of the center from the SMATE. And this is also one of the stuff which we try to transform whatever we do in the research to the industry part of it. So this is some of the collaboration which we are trying to right now, which we have. And we have a lot of JDP programs also. I see there are a lot of students over here. So we do also have joint doctoral degree program between some of these universities like University of Melbourne, NUS, Central, ECN, as well as RWTH, Aachen, wherein we do also have a joint collaboration. That means the students will try to get a 2 PhDs from IIT Madras as well as this one. So this is all overall about this particular center. Now I will just we will continue, and then I will try to leave it to Dr. Abhilash to continue on the one particular topic of this particular research vertical in the entire center perspective. Yeah.
Okay, am I audible and is my screen visible?
Yes.
Okay, fantastic. So thank you, Professor Sriram. He has given a very good overview of what all are the different aspects which the center looks at. So we'll look at one particular aspect which was focusing more on marine autonomy, and we'll talk more about what's going on with respect to marine autonomy, with respect to how it is aligning with the center. So my name is Dr. Abhilash Somayajula, and I'm a assistant professor in the Department of Ocean Engineering at IIT Madras. And I work on marine autonomous vehicles, and we have a lab here which is called Marine Autonomous Vehicles Laboratory. So we'll share some of the experiences of our laboratory and how they are getting aligned together with the Maritime Experiments to Maritime Experience Center. So our lab basically encompasses of three main areas, and these include implementing artificial intelligence-based autonomy algorithms on surface vessels. And we also look at traditional control theory or traditional methods of collision avoidance. And we also finally, the third leg is on hydrodynamics. We want to understand how the physics of the system can be understood better, especially with respect to fluid structure interaction. And we'll talk a little bit towards the end about how the future goals of our lab are looking and how they are aligning more with the center's goals and how can we take it forward in that direction. So let's talk more about the AI algorithms. So here we are interested in bringing out artificial intelligence-based algorithms for path following or for collision avoidance and all even for obstacle avoidance. So the difference between collision and obstacle is that collision is primarily related to dynamic obstacles, whereas obstacle avoidance means static obstacles. So we use what are called deep reinforcement learning based controllers. And these are primarily based on how humans learn. When we learned how to walk, we actually failed multiple times when we were trying to walk. And over time, we got the reward of what works and what doesn't work. And we are able to put all of that together in some way to finally learn how to walk. So ships are almost very similar. So the reinforcement learning algorithm, we basically ask it to track from one point to another point successfully. And when it is successful, we give it something of a reward. And when it does something which is not expected of it, we give it a penalty. And using these two approaches, it will try to learn the right behavior as to how to move from one waypoint to another. So what you see on the right-hand side are two graphs which tell you how the ship is able to move from the different waypoints across in an elliptic manner or in an 8 maneuver. And these are primarily done in our simulation environments. But that's not enough. We would like to see how this translates to the real world. And so we build autonomous surface vehicles. And one of the vehicles within our center is what you see on the right side. On the right side, you see a scaled model of a container ship. So which means this is the actual model of a real container ship. The real container ship would be about 230 meters long. And the scale model is with a scale ratio of 75.5, which makes it about a 3-meter model. And some of the sensors equipped for this sort of a test would be the IMU and a GPS. And these two would be fused together in order to localize the vehicle. So the vehicle will try to take both these measurements together, try to figure out where it is located at any particular time. And based on that, the deep reinforcement learning will guide it towards moving from one waypoint to the next. So we do implement these vehicles on real world. And what you see on the left side of the slide here is a picture of the IIT Madras lake. So we have a decently sized lake of about 300 meters by 100 meters, and we test our vehicles out there. So the vehicle you saw in the previous slide is being tested here, and we like to compare how does the simulation compare against the experiments. And we are very happy to see that they do compare very well, but we are also very excited to see that they don't exactly match. And when they don't exactly match, it gets us really excited because there is something still to learn from nature about the physics which we have not implemented correctly. Okay, so something else which we look at is static obstacle avoidance. So here is on the left, you see a picture which is depicting a static obstacle avoidance. And this is a work which has come out of co-guidance of a student between me and Professor Suresh Rajendran. And on the right, you see the same similar type of algorithms being used to avoid multiple obstacles in a row, and how can that be successfully performed. So that completes a little bit of what we have talked about AI algorithms. So we'll now move on to the next part, where we'll discuss a little bit about traditional approaches for achieving the same objectives. And we are very interested in seeing how the reinforcement learnings and other paradigms can be combined with the traditional approaches to yield us best of both the worlds. So that's what we'll look at now. So typically our ships are under-actuated, which means that these ships do not have actuators in all the degrees of freedom in which they need to work on. So you can think of this like a car, where a car can move forward and can turn around, but it can't move sideways. And because we do not have wheels which can make a car move sideways. So similarly, ships too are under-actuated in the sense that they can be propelled forward and backward. And similarly, the rudder on it can make it turn in either way, but it can't literally move sideways like a car. So when such systems need to be controlled, such systems are known as under-actuated vehicles. And we have to use a combination of guidance and control algorithms in order to track from one waypoint to the other. So what you're seeing on the picture on the left here is how can a vehicle track the path between two waypoints which are indicated in the red. And the main idea here is that since I can't move sideways, I'll aim myself towards a point which is slightly ahead of where I need to be. And that is what is called as a look ahead distance. So the main idea there is that this look ahead is where I'm aiming my ship, and my controller is trying to see whether my orientation of the vessel can be adjusted to that orientation which is desired from the guidance system. And as long as this is performed, we can see that the vehicle will smoothly enter into the trajectory which tracks the path from the left waypoint to the right waypoint. The main idea here is that since it is under-actuated, we have to rely on these systems, and we have to actually prove that they are stable in all situations. And there is a lot of mathematics which we are not incurring in these slides, as we are looking for a general public audience talk here. But obviously, when we want to actually implement them, we have to dig into the math. So once all of that is done, the result is what you see here. So here we have our Matsya ASV, or autonomous surface vehicle, which is tasked with following a square trajectory. And you see those 4 points on the plot on the top right. And as it keeps tracking each waypoint, you'll see that the waypoint turns blue, indicating that particular waypoint has been tracked. And this here is in using the ILOS guidance, or the integral line of sight guidance, coupled with a proportional derivative control to control the rudder. This is an experiment which was performed by my colleague, Professor Suresh Rajendran, so again in the lake. So we are still interested in not just controlling the vehicle, but also understanding how these vehicles actually behave in the water. So here he is performing a zigzag maneuvering test in the lake, trying to understand how maneuverable the ship is. And from this data, he will be trying to reconstruct, can we build better models of the ship, and can we actually be able to understand some better physics out of it. Okay, coming back to the collision avoidance problem, which we were discussing previously in the artificial intelligence-based methods, here we are trying to do the same using what are called traditional approaches. So here we are using a method called artificial potential fields, where the vehicle is drawn towards a goal and away from the obstacles. We set up this potential field and we try to simulate such encounters. What you see on the plot on the right, or plot on the left, is there are 9 different agents which are being put together in a congested environment, each being given a goal of its own. And we want to see what happens when multiple vehicles are encountering each other. So this is an example of 4 static obstacles, which are you're seeing in the red dotted lines. And then we have 9 dynamic agents which are trying to track all their paths and move towards their goals. Although such methods you would like to believe that they will work really well out of the box, we do see that when we test them over multiple scenarios and over 5,000 or 6,000 different simulations, they do have a good success rate, but still there are some shortfalls. So you do see that as the dynamic environments are becoming more and more cluttered in the plot on the right, we see that the success percentage does take a dip. And that gets us curious. What happens there? How can we design rule-based systems which are perfect in avoiding all possible encounters? And we are really interested to understand how can we design better rule systems for each agent. So here are some of the different algorithms which we did explore before we came to the previous slide's result. And we are interested in seeing how different artificial potential fields can lead to a slightly different behaviors. In fact, you can see that the plot on the top shows you that the avoidance doesn't happen until the vehicle is very close to the obstacle. Whereas in the second scenario, we are able to do a more natural progressive avoidance as you would typically see in a human-controlled vessel. So we are very happy to actually see that we had a student team develop out of our lab very recently. And in the last year, they have won very good competitions. So this here is showing a demonstration of a collision avoidance encounter from the small orange boat against the larger black boat. And they're trying to see how this can be done autonomously. So it detects the black ship on its own and tries to make a collision avoidance maneuver using the artificial potential fields that we just now discussed about. So I'm very happy to see such results where students are able to apply these things in real world competitions and even able to bag very good positions on them. The team got a third prize in this particular scenario. So based on this success, they also tried to participate in another competition, which is called the VRX or Virtual Robot X competition, which is organized by RoboNation. And here there were a set of perception tasks and station keeping and waypoint tracking and tracking tasks, which they were able to successfully complete. And our team was able to actually bag the first prize in this case and beating several international universities, including teams from NUS, Singapore, and so on and so forth. Okay, the third aspect of the lab, which is very important, is we look a lot on hydrodynamics. So here our interest is to understand the physics of the fluid structure interaction. We are not just interested in the autonomy part, but we are also interested in the modeling part. So unless until we understand the dynamics very well, we can't control them effectively. So the idea is to see how can we understand the physics of fluid and structure interaction together. So we have developed a simulation program which is nicknamed as Hydra. So Hydra stands for Hydrodynamic Response Analysis. And we are interested in seeing how well our simulation models do against experiments. So what you see on the plots on the bottom there are comparison between experiments and simulations for different regular wave conditions. How does the ship respond to it? And we are really interested in the vertical responses in this particular case, but we do also have validations for other modes as well. This tool is actually available for free for anybody to use around the world, and it can be accessed through this website, hydra.hydratech.in. You can even scan this QR code to actually get the link at a later point of time. So these tools are not only used for simple simulations, but we like to actually use them for very complex scenarios as well, to simulate complex scenarios. So what you see here is what are called parametric roll experiments. And ship, due to its symmetry to the port and the starboard side, which means the left and the right side, is supposed to not roll when it faces head-on waves. And since the symmetry is there, you don't expect the waves to cause you to perform a roll motion. But sometimes when the conditions are just right, you can see a large amplitude roll motion occur. And such sort of a phenomenon is an instability which occurs very frequently for container ships. So we are very interested to see whether our simulation program can accurately represent the real world dynamics. So on the left, you see the experiments performed in our wave basin in the Department of Ocean Engineering. And the right side emulates our reality or our simulation experiments from the Hydra tool. And we try to compare between the two of them, and we are very interested when there is some difference because there is some new dynamics to be learned. And we are also very happy when they match, which means that we are able to simulate it really well. Okay, something else which we look at is maneuvering in waves. So which means that as there is a new regulations in place, which are requiring the ships be outfitted with lower powered engines so that we can reduce the emissions of those ships. So one of the concerns in such a scenario is whether the ship will be effective in avoiding being thrown around by the waves. Can it overcome the waves naturally? So we do perform experiments in this direction to see what the dynamics of the system are when it is operating in waves. And if you look closely at the video, you'll see that when the waves come by from the beam side, the vehicle actually does experience a significant roll. And we are curious to see whether the vehicle can survive such conditions, how effective can it be, what can we do to make it more effective. Okay, some of the other things which we do are called system identification. So far I have been talking about how do I model the interaction between fluid and structure, but Mother Nature already gives us all of this when we perform an experiment in the lake. So the question here is, from the data which we garner from the lake, can we actually identify the physics directly? And this really falls under the artificial intelligence paradigm. And we are very much interested in learning from the nature. Can we build models which are much more accurate or which can augment the existing simulation models, and they can do better in the combination of both the worlds. So here we try to take our vehicles out into the lake and run them around quite a bit and collect data from them. And from this data, we would like to try to analyze and build models and see whether our built models are actually able to do as good as the real world experiments. So on the plots on the right, you see a comparison between the original paths and the identified models paths, and we are able to match pretty well. But still, over time, we do see a drift, and we are very curious to understand how we can make that better. So going forward, some of our future goals is to build a ship simulator. And in fact, one of this, we unveiled it at the recent open house event at IIT Madras. So the idea was that the public, we threw open the gates of IIT Madras to allow the public to come inside and see how the research is being performed at IIT Madras. So it was very happy to see a lot of children actually interact with our ship simulator, and we were able to actually instill them the curiosity of why is it so difficult to maneuver ships as compared to driving their dad's car or their mom's car. And I think you can see that in the picture where the children are really trying hard to maneuver the ships. And that was quite the fun to see and experience. Soon enough, this simulator, we're going to throw it open and allow for the public to interact with it through one of our web applications. Going forward, we are still interested in some of the ideas such as cooperative autonomy between multiple vehicles. How can multiple vehicles interact with each other? How can when vehicles have heterogeneous capabilities, how can we make them interact with each other so that they can get the best of both the worlds? Something else which we are interested in is how to do a cooperative autonomy between a surface vehicle and an underwater vehicle. Obviously, an underwater vehicle has some challenges associated with it, such as it cannot be getting a very good localization information as GPS is not available underwater. Whereas a surface vehicle does have the GPS available to it. So we are interested to see how we can combine both those robots to cooperate against each other so that they can get the best of both the worlds. This is a recent endeavor which has come up where we want to do a cooperative autonomy between the ASVs, But at the same time, we want to see whether the AUVs can be docked underwater permanently. Typically, to deploy an AUV, you have to have a ship where you go out there, deploy the AUVs, and the AUV finishes its mission, and then you have to retrieve these vehicles back. And that is quite the expensive procedure. And sometimes when the weather is not right, you probably are not in a position to go out there and do a deployment. So the question becomes, if the vehicle automatically docks underwater, when the time is right or when I need to collect the measurements, can I, with a push of a button from the shore, allow the AUV to take off, go do a mission, come back, dock, and give me back the data, and at the same time recharge its batteries as well? So this is a recent project which has come towards us, and the ME2ME Center is quite excited in this direction to see how we can build long endurance deep sea missions from these AUVs. And we will be looking at developing a inductive based charging system for such AUVs. And we are going to be collaborating with different disciplines across IIT Madras, including machine design, including electrical engineering, so on and so forth, which will help us achieve these targets over the next few years. Yeah, I think slides are stuck. No. All right. So this is the main overview of the autonomy part of it. So as I said, as Professor Sriram described, this is a one of the larger verticals in the ME2ME Center. And MAVLab is actually very happy to be part of this center and collaborate together with it. And we have been very generously been funded from the Ministry of Education through this center and also through other government agencies such as Science and Engineering Research Boards. So if you're interested, please do get in touch with us. We are always interested in hiring more people, more students, and we have some exciting projects upcoming in the next few years. So we'll be putting out some applications soon enough. So keep an eye out for that. Thank you. So stop the share.
Yeah, I think.
Yeah.
Would Professor Antonio maybe say a few words or bring up some discussion points that you might want to be addressed?
Yeah, thank you. So first of all, it's a pleasure to be here with all of you. As many of you know, I'm extremely fond of India and my cooperation with institutes in Goa and Chennai. I was in India last year twice. I'll be there in April and May, and then I plan to visit IIT Madras later in the year. So first of all, also a word of praise for to the IIT Madras team and the superb program that they are spearheading in India. It's truly fascinating. Now, I don't work so much with ships, but mostly with the marine robots. And for those that are hearing some of these things for the first time, the future is, I think there's a very good future ahead of us because, you know, all these systems, mostly marine robotics and others, have far-reaching applications in science, commercial applications, and societal issues. And in what concerns the scientific applications, I would like to say that marine robots are increasingly being used to explore the water column, the ocean floor, to study the interface between the sea and the atmosphere, marine habitat mapping with species recognition, water column species identification and biodiversity assessment. Another very interesting area is tracking of marine mammals and pelagic fish to assess the migratory and feeding patterns, adaptive ocean sampling to have a synoptic view of the underlying phenomena, so on and so forth. We need marine robots, groups of marine robots to do this. The commercial applications are also manifold. Geophysical and geotechnical surveying, braking with a classical ship and towed hydrophones, inspection and maintenance of offshore energy harvesting infrastructures and fish farms, Recently, I've been quite involved with other European partners on programs that have to do with autonomous marine transportation in ice-infested areas and inland waterways. Assessment and containment of pollutant spills at sea, which involves the cooperation between aerial and marine robots. So what are the main challenges? I think sustained autonomy is a very important factor. And Professor Abhilash mentioned this a little bit when he talked about having docking systems at the bottom of the ocean. You have to break with a tradition where you go out to sea with a big ship and a huge crew, and you are essentially chaperoning the babies underwater. You have to leave them there, and they should be left on their own. And they should exhibit some cooperative behavior, have the capability of doing some form of energy harvesting. And how can this be done? We don't know exactly how. I mean, we start to perceive the path, but there's a long way ahead. Then again, it was mentioned by Professor Abhilash, cooperative behaviors of groups of vehicles. They are extremely important. We are nowadays running a big European project where we have multiple vehicles, underwater gliders and surface vehicles, to map radioactivity underwater. But we also developed multiple vehicles to do geotechnical surveys. Another area that was not mentioned, but I think it's very dear to some of the students, it's what we call intervention robots. In other words, robots that can go underwater, and especially in offshore infrastructures, to actually hook themselves up to the infrastructures, do inspection. In other words, there's the interaction between vehicles and manipulators, and many others. Intelligent decision-making, leverage recent develops on AI. It's something that is always very exciting. And I would like to include a particular theme. We recently submitted a proposal to the European Union that may sound a bit crazy, but it has to do with morphing robots. And later, when I come there to India, I'd like to talk to Professor Suresh and Abhilash, whoever wishes to talk, about this idea of morphing robots, where we have robots that can operate on land, at the surface of the sea, underwater, and even in air. I think the future is quite smiley in what concerns the application of these morphing robots. So I don't want to monopolize the time. These were some brushes on this complicated and very exciting canvas of autonomy. Thank you.
Maybe if we can take some questions, we have a few in the Q&A box. That's okay.
Yeah. So the first one is
Professor Antonio, would you like to moderate the questions?
Yes. So the first question we have here is by Arnav Agarwal. Can the wave makers be used to create the waves as huge as storms? I don't know anything about this, so you guys will have to.
Sure. Yeah. So if you look at the facility, one of the facility which we are trying to create is 1:1 prototype scale. So yes, in those prototype scale, yes, within some limitations, up to 3 meters significant wave height, with a peak period of about 18 seconds, yes, we can able to create. And in the past, people have also created these huge storm waves in Europe, particularly in Germany as well as in Delft. So yes, it is feasible.
Thank you. The second question is, I don't know the name. This person is a Bopati. I am a Bopati studying third year Department of Safety and Fire Engineering in Excel Engineering College of Namakkal. Please clarify my question, sir. Now, there may be a mistake in the sentence. It reads as follows. Can any available maritime experiments related safety course or in-plan training program? I confess I can't make much sense out of this, but probably you'll be able to. Can any available maritime experiments related safety course or in-plan training program?
Okay, I think I can try to answer that a little bit, and maybe I'll yield a little bit to Suresh to do that. So, one thing which we do is, for example, for pilots or ship captains and masters, they do require a lot of training in order to know what decisions to take in difficult scenarios. And such sort of a things do happen with experiments, and you do try to see and understand how that can be understood better, and you can collect that data and actually even leverage it further to see whether newer algorithms can actually overcome that difficulties which humans might be having. So yes, there are a lot of possibilities in that direction. I do not know whether, particularly with respect to the fire engineering and Excel engineering, how does that relate exactly? I
Yeah.
probably am ill-equipped to answer that as well. Suresh, if you want to add anything, Professor Suresh, please feel free to add to it.
Yeah, I mean, I also don't have much to add, but I think the question is in the context of fire and safety. So probably you're talking more about in the like the fire and safety of the ship, which is most like on board of the ship. So it's kind of a marine engineering kind of point of
Question.
view, maybe. Yeah. So yeah, of course we have fire and safety. Of course, wherever there's industry, we should have a fire and safety officer. We have that in the ships, but we are not exactly dealing with that because we are mostly on the control part and the ship design. So it's more oriented towards naval architecture and ocean engineering.
Okay.
But other part of
Possibly they may be even thinking about how can fire safety be incorporated in maritime scenarios, and how can that be done, probably. But again, probably it's a little out of our area.
yeah, fire resistant materials, all these things are there, of course, but that's not, I think, that's beyond the scope of this center, right? I mean,
Yeah.
yeah.
Okay. Thank you. This one should be very easy for you. So it's from Angita Bhattacharya. From Prasant. Can you please elaborate more about the potential fields?
Okay. So potential fields are basically like, if you think of the charges, or maybe the best example to give is gravity. When you have two different masses which are close by, there is a potential field developed by the gravity which drives you to actually have one vehicle go around the other. But in a similar manner, in the potential fields application to our autonomous vehicles, we are trying to make the goal pull the vehicle closer to you, and we are trying to make it the obstacle potential in such a way that it repels you away from the obstacle. And a combination of these two is what is trying to drive you towards the goal while avoiding the obstacles.
Yeah.
Yeah, and I think one more stuff. I mean, the question is not clear. It says potential field. It can also be potential field of research
Could
in ocean engineering. So it's not
Oh, I
related
see.
to only one part, correct? So it is a
So
potential field.
maybe you should take over
Yeah.
that part.
So I think if you look at ocean engineering, there are different. Basically it is interdisciplinary. So it is most of people from India. They will know about civil, mechanical, electrical engineering, and other engineering. But ocean engineering, if you look at it, it's basically interdisciplinary field. So people with expertise in undergraduate in civil, or undergraduate in mechanical, or undergraduate in electrical and electronics or instrumentation can in fact have a lot of opportunities, I would say, in each of these. Either it is going to be, if it is going to be electrical, for example, electrical and autonomous, you have control signals and all those things we have today. If you are mechanical engineering, there is a lot of mechanical moving parts, either in offshore engineering or also in naval architecture part. Or if you look at the civil engineering, you have a lot of structures which are built both in the port as well as in the harbor. So of course, it is basically one of the things is it is interdisciplinary field. Each and every field can actually be incorporated over here. So that is one of the advantage of the ocean engineering field. So that actually answer. I hope that is what he means as a potential fields. Yeah,
Possibly.
sure.
So
Yeah.
maybe we have covered all the spectrum there.
Yes. Yeah.
Yeah. I think we covered the two possible interpretations, so we are safe.
Yeah.
So the next one now is by Angita Bhattacharya. How to learn naval architecture and coastal engineering, ocean engineering is vital for sustainable future.
Okay, Suresh, you want to take that?
Uh, sorry, what was the question?
Okay, I think
Sustainable
there may
future.
be two questions here. I think is stating or wants to be reassured that ocean engineering is vital for sustainable future. That's one thing.
Okay.
And then the next one is how to learn naval architecture and coastal engineering.
Yeah, the first question, it is pretty simple. I joined IIT Madras. We have a BTech in Naval Architecture and Ocean Engineering. We also offer Master of Science, MS in Ocean Engineering, MTech. Or you can also join for depending on what is your qualification. And other things, there are many other institutes all over India where you can do the bachelor's. I don't know what is your qualification now. So if you're looking for bachelor's, there are BTech in Naval Architecture and Ocean Engineering and Coastal Engineering offered in many institutes across India. And of course, I will just give you a brief glimpse of the sustainable future. Probably Sriram and Abhilash can talk more about it. So of course, blue economy, that is one of the things that is we are India as a nation, we are looking forward. A blue economy in the sense we are kind of exploring and exploiting the ocean for and at the same time it should be sustainable for the humanity, for the countrymen. And there are a lot of things that we have to address. So far, if you look at the shipbuilding, or if you're looking at the coastal engineering part, there are a lot of gaps that we have to address, and that is what actually this center is trying to do with these kind of facilities that we are building in IIT Madras. So of course, this is because if you look at our ocean, is like we have ours is the country with a vast coastal line, and 90% of the ocean is still untapped. So there's a lot of potential there, but at the same time, we have to use it in a very sensible manner. We have so that it is sustainable for a long. It is sustainable for the whole humanity and for the same time ecosystem. All these things we have to take into account. So probably Sriram and Abhilash can add more to that.
Yeah, I think mostly Dr. Suresh has addressed. So if you are, it doesn't matter, as I told you, it is interdisciplinary field. So if you are already done an undergraduate, you are most welcome to reach us for your post-graduation in this entire field of ocean engineering or coastal engineering as well as naval architecture. Yeah.
Thank you. So the next question by D. Abhinav. In deep reinforcement learning, how can AI algorithm be penalized or rewarded? What exactly stands as penalty or reward for a machine?
Okay, maybe I can take that question.
Yeah.
So in deep reinforcement learning, typically the reward would be when you actually get to the goal or when you're trying to approach the goal, and there are different metrics to measure this. One metric could be what is the distance of the vehicle from the current time step towards the goal. Also, something when you want to track a particular path, you might be interested in how far away from the path am I, or how much is my current direction different from the direction it should have been. So these sort of metrics usually govern the reward system. And the penalty would be, let's say that I have an obstacle coming at me. I'd like to know how close to the obstacle am I. I would like to penalize my system when it tries to move closer towards the obstacles. And I'd like to reward it when it tries to avoid them and go towards the goal. So these sort of reward functions and penalty functions are what will allow the agent to learn or reinforce the behavior so that it can do this effectively. But the caveat is designing these rewards can be quite complex. And sometimes, if we are not very careful, you can come up with very alternative solutions which you would not have thought of, but the machine would have learned based on the reinforcement. So it's very important to figure out the right rewards And how to tune those rewards is quite the big challenge, which still, in my opinion, is not fully solved. And there is sufficient research which is still going on in that direction.
Yeah, thank you. Well, my only comment is that as it stands, deep reinforcement learning is not an ad hoc method where you simply import some basic rules that may seem logical and you play with them. No. Currently, reinforcement learning brings together many things like the dynamics that hinges upon decision Markov processes, then optimal, let's say optimal control theory, Bellman's equations and stuff like that. And then you have the beautiful thing of approximating the solutions using neural networks, and then there you have the deep neural network. So I think it's a very interesting topic because it mixes traditional stuff with the new vision of what lays ahead. Okay, thank you. So now we have an anonymous attendee. Sir, marine conditions are different from lake conditions, which are calm. How reliable are the experiments conducted in lakes? And I'm assuming if you want to extrapolate to marine conditions.
I think here we can talk about a twofold approach. So obviously from the autonomy side, when we were showing you the experiments in the lake, there we were primarily relying on the autonomy algorithm doing the obstacle avoidance particularly effectively. When we want to look at the effect of the environment on the vehicles, we won't be testing them in the lake. We'll be testing them in our wave basin, which was shown by Professor Sriram. There we'll be subjecting the vehicle to different types of waves in a controlled environment and observing their behavior exactly. So it's a combination of these things which actually comes together to form a good extrapolation from experiments to the reality. And rather than just looking at one aspect, it's a combination of different experiments which look at different parts of the dynamics of the system, which tie up together to give you a reliable answer at the end.
Okay. So the next one, it's again an anonymous person. Can we have more details about deep water basin, particularly 9-meter pit? How the wave generation here, pedal or piston?
Yeah, so this is under preparation right now. We are trying to plan the entire stuff, and it will be based on the piston type wave maker. So we want to generate in a water depth of 5 meter, like in a prototype condition. So normally it's a shallow water effect. So we will go for a piston type wave maker, and the deep pit is under preparation right now. So the total depth is 9 meters. So the below the 5 meter there will be about 2 meters. So that was the plan right now. So the tank depth is basically 9 meter over the entire part. So then we will, once we install, I mean, once we have the space right now, we are in the process of constructing. So once we have realized, then we will try to give the more details about the facility. Yeah, sure.
Okay, thank you. Now we have another anonymous attendee. What is the possibility of using combination of both the maneuvering mathematical model and AI algorithm for path tracking?
Okay, all right. So definitely there is quite the scope for combination between those two over there. And something which suddenly came to my mind as I was reading this question was there is this new approach where you want to look at something called as imitation learning. And you want to look at data from where actual pilots have taken certain decisions to actually avoid collisions with other ships. And you'd like to learn that experience and bring it into your reality. So obviously the two sides of the coin here is when I want to check upon this, I need a strong model or a simulation model to test upon it. And the AI algorithm is really looking at how can I learn these complex patterns or complex behaviors and then can see whether it's able to apply really well. So a combination of the two is really important. And something which is at the combination of the two is still something called physics informed decision making or physics informed modeling, where you're not just looking at the data as a data, but trying to understand whether it is conforming to certain physical laws. And using those aspects, you're able to actually build better or more reliable mathematical models for your simulations. So it's a constant endeavor to see whether the dynamics which we are simulating can be improved to match well with reality. And AI actually does help quite a bit in uncovering those dynamics for which we may not be having proper physics models yet.
Thank you.
Suresh, if you would like to add something to that, feel free to jump in.
Yeah, so I think I don't have much to add to what you said. So this question is mostly about the combining the maneuvering mathematical model and AI algorithm. So one thing is that when we use this AI, which is basically in this case, as Professor Abhilash has mentioned, reinforcement learning. So it's a kind of a paradigm, one of the paradigms of the machine learning, where it's not like a supervised learning where you don't have any data, train on some data and test it on the rest of the data. But here, as the algorithm goes, it generates its own data and learns from its own experiences. So in that case, we are assuming that we don't need any mathematical model, which is basically data driven. It's not a model based controller. So the agent learns by itself the dynamics, and it is able to control, like the car. So if you have a self-driving car, initially you are putting an RL algorithm, it will make a lot of mistakes, and slowly it will learn. But the problem with the limitation is that if it's with simulation, it works, because in a computer simulation, you don't mind how many times your character dies, it doesn't matter. But in the case of real car or ship, basically it matters, because it is going to collapse or capsize. We are going to lose the entire physical system. So in that case, we need a combination of, like what already Professor Abhilash mentioned, like imitation learning, where we learn from the human, or we have some kind of a basic model on which we train the system, and then on further deploy it on the real environment, so that that uh, whatever damages it is costing the physical system is completely reduced and within our acceptable limit. So maybe that is another point we can think about.
Thank you. So there's a question by Pallav Ranjan. Is the center planning to indulge into research on nature-based solutions for coastal resiliency, understanding coastal biophysical interactions, morphodynamics, marine CDR, etc.?
Yes, yeah. So we are already working on the nature-based solutions, particularly the wave vegetation interaction. We are trying to develop the models. We do also have some of the models that can address this aspect. As well as we are also doing experiments. We are also having some, we are already having Indo-German project on these nature-based solutions too. So yes, we are already working on this entire area. But except the biophysical interaction process, which is more about the more interdisciplinarily with the biological stuff, we are dealing only mostly on the engineering solutions.
Yeah. Okay. So there's a question by R. Eshwar. What are the similarities and differences between the numerical models developed by Professor Sriram and the Hydro tool developed by Professor Abhilash?
You want to take it? I know who this boy is. He's a student in our class. So.
You should have asked it in the class itself, right?
No, that's fine. But the mathematical base is similar.
Maybe I'll try to answer that a little bit more differently. So I'm more interested in the dynamics of the structure. So I'm really interested in simulating nonlinear behaviors of the structure when it's interacting with the fluid. And Professor Sriram's models are really trying to capture the free surface effects exactly, whether we are able to get the waves to be as realistic as possible. But that comes at a computational cost. So it's a balance between the two, whether I want to invest computation more on the fluid side or whether I want to invest more on the structure side. Since I am more interested in the structure side, the waves which I'll be using will be primarily be airy wave theory, whereas when Professor Sriram is trying to simulate the similar exercise, he'll be trying to do something called nonlinear, fully nonlinear potential flow, or CFD methodologies, where he can bring in the more accurate physics to capture the wave effects more accurately. But you have to understand that at the end of the day, you have a limited amount of computation power with you. So you have to choose well into what process you want to put that computation on. And I think that's the balance which needs to be struck right.
Thank you.
Yeah,
So
it's fine.
we have a final question, and I'm encouraging other people to post other questions. It goes as follows. Any future developments for offshore wind lab testing, like wind generator together with wave generator in the facilities?
Yeah, actually, in fact, this is one of the suggestion which I received from my colleagues in abroad, because they already have the wave and current testing facility. But around the world right now, the renewable energy is quite popular. So whether you can able to put a wind testing facility along with the wave generator, yes, strictly it is feasible, but the cost would be of very high, because you need to generate the sustained wind. So this is for the future to decide. As of now, not, but in the future development is feasible. Yes. Yeah.
Thank you. So I don't see any further questions. Please rush in case you wish to pose one question. And I don't see any more questions. Okay, I don't see
Yes.
them.
Okay.
Yeah.
So
So
maybe we can end our session if there are no more questions. So
Yeah.
thank you, everyone. Thank you, Professor Sriram, Professor Abhilash, and Professor Suresh, Professor Antonio, for taking your time and doing this for
Yeah,
us.
it's a
And
pleasure.
thank you, audience, for all those really nice questions. And in case you do have any questions, I've dropped our social media links in the chat box below. You can always get in touch with us, and we will put you in touch with the ME2ME group. So thank you, everyone, and wish you a very good night.
Yeah.
Yeah.
Thank
Thank
you.
you. Thank you.
Yeah.
Thank you.
It was a
Thanks.
pleasure.
Thanks.
Talk to you soon.
Thank you.
Bye-bye.
Thank you, Professor Antonio.
Bye bye.
Thank you.
Bye-bye.
thank you,
Thank
Professor
you.
Antonio. Take
Take
care.
care. It
Thanks.
was a pleasure. Bye-bye.
Bye-bye.